In this video, we introduce the Dantzig-Wolfe decomposition method, which is used to solve large-scale linear programs. We start by reformulating our LP using a Dantzig-Wolfe reformulation. So let's consider the following linear program. We have minimize C transposed X, subject to AX is equal to B, and X belongs to some set X capital, which is a polyhedral set, and for now assume that this is a bounded polyhedral set. In other words, X is a polytope. Also assume that if we dropped the constraints AX equals B, then the resulting LP would be very easy, meaning that this set X is described by some easy constraints. So let's call these easy constraints. On the other hand, having these constraints AX equals B makes the problem more difficult. So we'll call these constraints the complicating constraints. To obtain the Dantzig-Wolfe reformulation, we are going to use the representation theorem for easy constraints. So assume that x1 through xt are the extreme points of the set X. Then by representation theorem, every point from the set X capital can be represented as a convex combination of these extreme points. So we have X is equal to the summation of lambda j's xj's for j between 1 and t, where the summation of lambda j's is equal to 1 and all lambda j's are greater than or equal to 0 for j between 1 and t. So now to obtain the Dantzig-Wolfe reformulation, what we are going to do, we will plug in this representation for X in our formulation. So instead of X, we are going to write a summation of lambda j's xj's. As a result, we are going to obtain the following. So our objective was C transpose times X. Now, once we replace X with this summation here, lambda j's are scalars, and then C transposed times this sum is going to be equal to the summation of lambda j's C transpose times xj's for j between 1 and t. So let me separate the scalar here from the scalar product. And actually, let's switch the order. First, we'll write down C transpose times xj, and then lambda j, subject to, when we multiply a by x and replace x with the summation of lambda j's xj's, we will have a similar situation. We will have the summation of a times xj's multiplied by lambda j's for j between 1 and t. This is for the left-hand side of this constraint, and the right-hand side remains b. And finally, the fact that x belongs to the set X capital is described by these conditions that we have on lambda j's. So the summation of lambda j's for j between 1 and t is equal to 1, and then lambda j's are all non-negative for j between 1 and t. So this is exactly what we call the Dantzig-Wolfe reformulation. And we can see that this is an equivalent representation of our original problem, which assumes the knowledge of all the extreme points of the set X. So now extreme points are given, right? So we can compute C transpose times xj's, we can compute A times xj's, and now lambda j's become our variables, and by varying lambda in this feasible set right here, we'll obtain exactly the feasible set of our original formulation. So any x from the feasible set of this formulation can be represented as a feasible point for this formulation in terms of lambdas, and then every feasible point of this formulation corresponds to a feasible point of the original formulation. And the objective value for these alternative representations will be the same. Therefore, we can use the Dantzig-Wolfe reformulation in place of the original formulation and solve it in order to solve our original LP. Okay, we can see that we can reformulate our original problem using the Dantzig-Wolfe reformulation, but the question is, why do we want to do that? To produce a Dantzig-Wolfe reformulation, we actually need to have the information about all the extreme points of the set X. And we know that a polytope can have a huge number of extreme points. So why do we need to go through this pain here and formulate the Dantzig-Wolfe problem instead of just sticking to the original formulation? And the reason is that when we do the Dantzig-Wolfe reformulation, we don't really explicitly mention all the extreme points of our set X here. Instead, we will start with a small subset of extreme points of X capital in this formulation in order to obtain what we call the restricted master problem. Then we'll try to apply the column generation framework in order to obtain other extreme points of X, which will help us improve the objective of the restricted master problem. So this is the idea of the Dantzig-Wolfe decomposition method. So let's call this problem the master problem. And again, because we have way too many extreme points in general, we are going to focus on what we call the restricted master problem. So we go from this formulation to a formulation focusing on a limited number of lambda j's. So we'll have the summation for j in some set I. This will be the set of indices we start with of C transposed xj's times lambda j, subject to the summation for j in the set I of axj times lambda j is equal to b, then the summation of lambda j's for j in the set I is equal to 1, and all lambda j's are non-negative for j in the set I capital. So this is what we call the restricted master problem, or RMP for short. So let's denote the optimal objective of the restricted master problem by z bar. Obviously, z bar is going to give us an upper bound on the optimal objective value z star of the master problem, because a solution to the restricted master problem is feasible to the master problem, and then there may be some good columns that we can add to the restricted master problem in order to improve the solution. Therefore, an optimal solution to the master problem can only improve upon the solution to the restricted master problem and can never be worse. Now, assume that we solved the restricted master problem and we want to determine if this optimal solution to the restricted master problem is also optimal to the master problem. So for that, we are going to check the reduced costs of all the non-basic variables, and when we compute the reduced costs, we'll need the optimal values of the dual variables. So let's denote the optimal values of dual variables by y's for the first set of constraints here, and then we also have the convexity constraint that we have from the representation theorem, and we'll denote the corresponding scalar dual variable value by alpha. So the vector y here has as many entries as the number of rows in the matrix A. Let's assume that it is given by m small as usual, and alpha is a scalar. So to compute the reduced cost for a variable lambda j, let's see what we have in the corresponding column. In the objective for lambda j, we'll have C transpose times xj, and then for the constraints, we will have m entries given by axj, and then we'll have one more entry given by 1 here, so which is the coefficient for lambda j from the last constraint. So this is our column that we need to focus on when we compute the reduced cost and when we formulate what we call the column generating subproblem. So the goal of the column generating subproblem is to find the smallest reduced cost and then see if that smallest reduced cost is less than 0. If it is, then we obtain a new column that we want to generate for our restricted master problem. Otherwise, if the smallest reduced cost is non-negative, then we conclude that the current optimal solution to the restricted master problem is indeed optimal to the master problem, and we are done. So our column generating subproblem is to find the smallest reduced cost, which means that we are minimizing for j between 1 and t, and the reduced cost is given by the difference of the coefficient we have in the objective and then the vector of optimal dual variable values multiplied by what we have in this column in the constraints, right? So we obtain minimize C transposed xj minus y transposed multiplied by A times xj, and then minus alpha times 1, which is just alpha. So we need to find the smallest of these t reduced cost values, meaning that we need to find the extreme point of the set x capital. Recall that xj's are the extreme points of our set x capital that minimizes this objective right here. So we can equivalently reformulate this problem as a linear program of minimizing C transposed times x minus y transposed times ax minus alpha over the set x capital, right? Because we are looking for the best extreme point of the set x capital with respect to this objective, which is equivalent to this linear program right here. And remember, we made the assumption that the set x capital is described by the set of what we call easy constraints, meaning that this problem is very easy to solve. So let's reformulate our column generating subproblem as an equivalent maximization problem. So we maximize over the same feasible set x capital the negative of the objective of our column generating subproblem, which is y transposed times ax minus c transposed x plus alpha. Let's denote the optimal objective value of this problem, which is again a maximization version of our column generating subproblem, by z hat. And next we will show how we can use this z hat value in order to obtain a bound on the optimal objective value of our original LP. And recall that a feasible point for our original LP had to belong to the set x capital, and also it had to satisfy the complicating constraints ax equals b. So let's consider a feasible solution to our original LP, and for such a point we have the following inequality. So we have y transposed times ax minus c transposed x plus alpha, which is the objective for this LP right here, right? So, and because the point x is feasible for this LP, and z hat gives the optimal objective value, we have the inequality less than or equal to z hat. Alright, so this is equivalent to stating that C transposed X is greater than or equal to Y transposed AX plus alpha minus Z hat. So now let's see what we have in this expression right here. First of all, we assume that this point X not only belongs to X capital but also satisfies the complicating constraint, meaning that AX is equal to B. So we can replace AX here with B. So we obtained here Y transposed B plus alpha, but then what is Y transposed B plus alpha? It's nothing else but the optimal objective value of our dual LP. That is the dual of the restricted master problem. And we know that the optimal objective value for the restricted master problem is Z bar, and the optimal dual value must be exactly the same. So this whole thing here is equal to Z bar. So we obtain Z bar minus Z hat here. And this expression Z bar minus Z hat, which is the difference between the optimal objective value for the restricted master problem and the optimal objective value for the column generating subproblem in its maximization form, this gives us a lower bound on the objective value for this feasible solution to our original LP, right? Since this inequality holds for any feasible solution to our original LP, we obtain the inequality Z star is greater than or equal to Z bar minus Z hat, right? So the optimal objective value for our original LP is at least as large as Z bar minus Z hat. Also, we mentioned before that when we solve the restricted master problem, Z bar gives an upper bound on the optimal objective value for the original problem, which is the same as the optimal objective value for our master problem, right? Therefore, we can expand this inequality here to the following. So we have Z bar is an upper bound on Z star, and Z bar minus Z hat is the lower bound on Z star. So as a result, we obtain these nice bounds here for our optimal objective value for the original LP. This bound can be used to see how far we are from the optimal objective value after every iteration of the Dantzig-Wolfe decomposition framework, and this is something that we will always use when we apply this method. To summarize, a step of the Dantzig-Wolfe decomposition method consists in solving the restricted master problem first, which only uses a small subset of the variables of the master problem. Then we try to generate the column by looking at the smallest reduced cost, which is obtained by solving the column generating subproblem. If the optimal objective value for the column generating subproblem is less than 0, then we obtain an entering column for our restricted master problem. Otherwise, if it is greater than or equal to 0, then we conclude that the current optimal solution to the restricted master problem is also optimal to our master problem and as a result to the original problem. So here we actually consider a maximization version of the restricted master problem. Also, we use this Z hat value to obtain an estimate of the optimality gap at the current iteration of the Dantzig-Wolfe decomposition. We have shown that the optimal objective value for the original problem given by Z star is sandwiched between Z bar minus Z hat and Z bar, where Z bar is the optimal objective value for the restricted master problem at the current iteration, and z hat is the optimal objective value for the column generating subproblem restated as a maximization problem. According to this inequality, z hat is very useful in determining how far we are from the optimal objective value at the current iteration of the Dantzig-Wolfe decomposition, and in particular, when z hat is equal to 0, we can clearly see that we close the gap and we obtain the optimal solution to our problem.